All right, hello and welcome, future engineers. For your first deep dive with us, we're going to talk about a material that is, and I mean this literally, all around you, plastics. They're cheap, they're light, they're strong, and they're just so incredibly versatile. Today, we're going to unpack the science behind them, starting from their tiniest building blocks all the way up to the properties that make them so darn useful. So let's jump right in.
So to get us started, I've got a question for you. Think about the average car on the road today. Compared to one from just 20 years ago, it's gone through a huge transformation, and it's lost a lot of weight. So what do you think? What's the secret sauce that made that happen?
Nope, you got it, plastics. By swapping out heavier, traditional materials, plastics have helped cars shed about 200 kilograms. But that's not even the whole story. Here's the real kicker. That weight saving means each car saves around 750 liters of fuel over its lifetime. That is a massive impact, and it's a perfect example of why understanding these materials is so critical for you as engineers.
Okay, so here's our game plan for today. We're going to start with what plastics actually are. Then we'll zoom way in on the polymer chains that they're made of. We'll follow their journey all the way from crude oil, look at the two major plastic families, and then see how their internal structure changes everything. And finally, we'll get into the really cool stuff, how temperature can turn a plastic from something hard like glass into something soft like rubber.
All right, first things first, what are we even talking about when we say plastic? Well, the name itself gives us a huge clue. It comes from the old Greek word plastikos, which means to form or to mold. And that right there, that's the whole magic of it, their incredible ability to be shaped and formed into almost anything you can imagine.
So here's the deal. When we say plastic, what an engineer or a chemist is really talking about is a polymer. They're pretty much interchangeable terms. But, that just leads to another question. What in the world is a polymer? Let's break it down.
Okay, so now we're getting into the absolute fundamental building blocks of every plastic out there. This right here is the key concept. I mean, if you get this next part, everything else we talk about is going to click right into place.
So it all starts with one tiny thing, the monomer. Think of it as a single, small molecule, the basic unit that repeats over and over again. The best way to picture this is as one single link in a chain. Just one. Simple, right? But this little guy is the foundation for everything.
And now, what happens when you take a whole bunch of those single links, those monomers, and you chemically connect them all together? End to end? Bam! You get a polymer. The name literally tells you what it is. Poly means many, and mer means unit. So a polymer is just one giant molecule made of many, many repeating units. It's the whole chain.
And this process of linking them up is called polymerization. You start with a big soup of individual monomers just floating around. Then, a chemical reaction kicks everything off, and they start linking up, one after another, forming these incredibly long, tangled chains. And it's those long chains that give plastics all their unique and useful properties. Okay, so we know we need monomers to make our polymer chains. But where do the monomers themselves come from? Well, for most of the synthetic plastics you and I use every single day, the story starts deep underground with a raw material I'm pretty sure you've heard of.
Yep, crude oil. But hold on, because this is where it gets surprising. You probably think of oil as fuel, right? For cars, planes, and heating. And you'd be mostly right. A whopping 87% gets burned for energy. But check this out. Only about 4%, just a tiny slice of the whole pie, is actually used as the raw material to make all the plastics in the world. It's a small piece, but boy is it a valuable one.
So how do we go from that thick, black gunk to our tiny monomers? Well, first, the crude oil goes through what's called fractional distillation. Basically, they heat it up, and different parts separate out at different temperatures. We grab one of those parts, a fraction called naphtha. Then we put the naphtha through a process called cracking. That's where we use a ton of heat to literally smash its big, long molecules into smaller, more useful ones. And those pieces are our monomers, all ready for polymerization. Now that we know what plastics are and how they're made, let's talk about the two big families they all fall into. Think of it like a major fork in the road, and everything comes down to one simple question. What happens when you heat it up?
So on one side, you have thermoplastics. The best analogy here is a chocolate bar or a plastic water bottle. You can heat it up, it gets soft, you can reshape it, and when it cools down, it's hard again. That's because their polymer chains are just held together by relatively weak forces. On the other side, you have thermosets. These are more like baking a cake. Once it's baked, the shape is set forever. You can't just melt it back down into batter. If you heat it too much, it just burns. And that's because its polymer chains are locked together with super strong, permanent chemical bonds. This is a huge deal, by the way, for recycling. Thermoplastics can be recycled. Thermosets generally can't.
Okay, let's zoom in even deeper. It's not just about how the chains are linked to each other. The way the chains are arranged and packed together makes a world of difference. This internal organization affects everything, from how strong the plastic is to whether you can even see through it.
First, you've got what's called an amorphous structure. And the best, and I mean the best analogy for this is a big bowl of cooked spaghetti. The polymer chains are a totally disordered, jumbled, tangled mess. There's no order at all. And because they're all mixed up, light can usually pass right through, which is why these plastics are often transparent. And the exact opposite of that is a crystalline structure. So, to stick with our analogy, this is like a brand new box of uncooked spaghetti. All the polymer chains are packed neatly, side by side, in these highly ordered, parallel regions. And because of that perfect order, they tend to scatter light all over the place, which usually makes the plastic look cloudy or opaque.
But, and this is a big but, in the real world, almost no plastic is perfectly one or the other. Most plastics are actually semi-crystalline, which just means they have both. You get these little highly ordered crystalline regions, our uncooked spaghetti, floating around inside a bigger, messy matrix of amorphous chains, our cooked spaghetti. It's a mix of both worlds in one material.
All right, for our last big topic, let's put all these ideas together and look at what is probably one of the most important concepts for any engineer working with plastics: how temperature changes everything. This is where it gets really interesting.
Let's focus on those amorphous parts of the polymer, the cooked spaghetti regions. They go through a critical change called the glass transition, and it happens at a specific temperature called the glass transition temperature, or TG for short. Below this temperature, the plastic is hard, stiff, and brittle, like glass. But take it above that same temperature and the very same material becomes soft, flexible, and rubbery. Understanding a material's TG is absolutely essential.
So what's happening at the molecular level? Let's switch from spaghetti to snakes. Above the TG, it's like a warm day for a pile of snakes. They have lots of energy, so they can wiggle around and slither and slide past each other really easily. This movement, this mobility on a tiny scale, is what makes the material feel soft and flexible to us. But as you drop the temperature below TG, it's like a sudden cold front moves in. The snakes lose all their energy and they get frozen in place. They're still all tangled up, but now they are locked solid and rigid. So if you try to bend the material, those chains can't move to relieve the stress, and the material just snaps. It's brittle. That's the glassy state. And if you were to plot this on a chart, this is what you'd see. As you start heating a semi-crystalline plastic, you first hit this little step change. That's your TG, the glass transition, where the amorphous, cooked spaghetti parts soften up. If you keep pumping in the heat, you eventually hit this big, sharp peak. That is the melting temperature, or TM. And that's the point where the ordered, crystalline, uncooked spaghetti regions finally break apart and the whole thing turns into a liquid.
So, there you have it, from single molecules all the way to melting points. And the crucial point here is that understanding this stuff, knowing that the very same material can be a rigid glass or a flexible rubber depending on the temperature, that's your new superpower. This is the knowledge that allows an engineer to look at a problem and choose exactly the right material for the job. So the real question is, now that you know, what will you do with that power? How will you choose the right one?